that, sorry, this is the flow sheet blocks, which we already covered. And that is what we are going to do next. To prove the case, Bond asks Davy to simulate and check the volumetric flow of the required water at various pressures between 0 to 10 bar G, so that he can evaluate the required flux sizes. So if I want to know a physical property at many different conditions, the easiest way to do this is by using the case study tool, which I'm going to show you how to do that. So a case study consists of manipulating an independent variable, then recording the response in a dependent variable. Okay, so let me just go back to the HYSYS here. I'm going to just reset this back to atmospheric pressure. And I'm going to run the case study tool, which is on the home toolbar. Case studies is right here above the analysis tab. Just click on it. Click on add. And I have case study 1, which now allows me to define the variables that I want to see. So the first thing to do is to select the independent variable. So I must click on find variables. So I'll choose what I want, which stream I want, which is utility water. Double click on that, and it shows all the properties that I can manipulate. So in this case, it will be pressure. So I just select this and click on done. So I only have one manipulated variable. And then the dependent variable here would be, again, click on find variables. Now click on utility water. Here we are going to look at the mass density. So you can see the density difference. And you might also want to just look at the volumetric flow rate. So it's something like liquid volume flow at standard condition. No, it's not this one. I think it should work in this case because it's liquid. So I'm just going to click on done. And then I'm going to move into case study setup, the second tab, which is where I decide how many steps I want. So what I need to do is in here for start, I will type in the start value. The ending value will be 10 bar G. So maybe 1103.325. And then I want to have like 10 steps. So now maybe it's 11. So the difference is 100. So the step size is 100. And then I can just click on and take this reset after run, or click on this. Then it will just decide whether it resets to the start after it runs. And then I just click on run. So the status shows success. We look at the result. So this is the density at the 11 different cases. This is a flow rate. And then I can also click on plot. So I can choose the variables on the plot. So I'm going to choose on pressure as the x-axis, and then the utility mass density at the y-axis. You can see that the pressure has changed very little. The density has changed very little. In fact, even the decimals don't show a difference until 7 bar G. I can also view a liquid volume flow. You can see the liquid volume is basically the same. It's so small that it cannot be seen. Right? The difference is so small. So this is what we call a case study. And it allows us to vary a certain parameter and to look at how it affects another parameter. So I've shown you the case study result. So in this case, right, it will not make any sense to just get a second pump. You should just buy one pump and that's it. So a little bit of notes about how to select the correct fluid package. The correct fluid package selection depends on what components you have, what is your temperature in the flow sheet, and what is your pressure in the flow sheet. So like there are many like flow charts or many guidelines on what to choose when. But this is one of them. So for example, we start from here. classify all the components you process, your gas, non-polar, associating, solvating, electrolyte. Is it all gas or non-polar? If yes, then you choose Peng Robinson, SRK. If it's electrolyte, you choose this. If it's not, then so and so on and so forth. So this is some guideline about what, how do you choose the required fluid package. And there are also some choices that are for specialized applications like gas dehydration. So maybe the best is sour water stripping, which is a refinery process. Maybe sour beer. Cryogenic gas processing, maybe is air separation, atmospheric crude distillation tower, ethylene tower, high hydrogen, and so on and so forth. So there are like some specialized fluid packages that are designed for these applications. So this is a case study without example that I showed just now. So like you can see that the mass density, the unit is very small, but this is actually like 1007 over here, and this is like 1008 over here. So the density has only changed by 1 if we increase the pressure by 10 bar. All right. So second tip I want to share is always cross-check with something you already know before you proceed with any simulation. Because if you can catch your mistakes early, they will be much less painful for you in the future. You want to catch the mistake as early as possible if there are any mistakes. You don't want to like catch a mistake at the end of the project when you want to submit to your lecturer or to your boss or something. Then you won't have the time to fix it. Right. So I'm just going to try one example with butane. I'm going to try one example with butane, and I'm going to compress butane from 10 bar to 20 bar. Sorry, I'm going to I'm going to compress butane from 10 bar to 20 bar using a pump. So let me show you this. All right. So I'll just start a new case study. I need to start a new case so I don't overwrite this old file. Okay, in this component, I'm just going to put butane. It should put N butane. And then I will just put a second one, which is high butane. Okay, in the fluid package, I will select, since it's oil and gas again application, I'm going to select Peng Robinson. And I will go into the simulation screen. I will put in one stream, which is just for one, a pump to 2. This butane, this stream will consist of, let's say, temperature of 50 degrees, pressure of 10 absolute bars, and composition will be 75% butane, 25% I-butane. And then you can click on equalize composition. Then it will normalize the composition to each one. Or you can click on normalize, then you will normalize to get total equal to 1. So in this case, right, just now I type 75 and 25. You click on normalize, and then you will make it 0.75 and 0.25, so that the total is 1. So this is very helpful too in case that for some reason your composition doesn't end up to 1, maybe because of some errors or some measuring issues or something. So, and I'm just going to make this 100 kilomole per hour. So now this stream is fully specified. Choose this pump. Connect this pump to 1. And then connect the outlet. I need energy stream, so I'll just go out edit. Okay, so I'll define the outlet pressure as 2000 kPa. So you get pumping you get this butane mixture being pumped from 10 bar to 20 bar. Temperature increased by about 1 degree. The power is 4 kilowatt, and nothing special, everything works, right? But what happens if, let's say, I change the inlet condition? Let's say it wasn't 50 degrees. Let's say it's 100 degrees. You get some issue. The issue given, look at the warning, vapor in inlet stream. So I'm wondering why is there vapor in the inlet stream, right? Let's go back to the phase diagram of butane, which I'm just going to show it here. You can see that if I were to have 10 bar and 100 degree, this will be in the gaseous phase, and you cannot pump the gas. You cannot pump the gas. You can only pump liquid. And because the mixture is 75% butane, it's most probably also somewhere to be very near this point. And if I look closer to using an engineering toolbox link, which I'm shown in the chat, you can see that at normal conditions, about room temperature, at 10 bar, butane is a liquid. But above 79.5 degree, butane turns into a gas. So it now creates errors if I try to pump it. And this is sort of the common sense that we need to have a sense of before we when you're doing. So in case you get some error, you don't panic. Oh, wow, what happened? What happened? Oh, it turns out that we are trying to pump a gas and you can't. Another clue would be to look at the density. Usually a gas density is around 10 to 100 times smaller than the liquid. So for example, right, you look at this density is 500, goes down to 25. So there's a 20 times drop. So it looks like there's going to be a phase change in the substance. So if I go back to this stream, and we set the pressure to, and we set the temperature to 50 degrees, I look at the calculated density is around 500 kilogram per meter cube. I increase the temperature to 100. I go back to property. The density has dropped to around 22 from 537. So that is a clue that there is some phase change happening that we did not expect. All right, and that is why your pump is not showing an error. Because having vapor during the pump will cause something like what we call cavitation, which will damage the pump in real life. So that's why it's showing an error.